Hello, my name is Sydney Walker,
I'm Anna Grace Aiello.
I'm Landry McRoy.
I'm Brooke Quintana.
and we're part of the Galaxy Classification Dark Energy team. Today, we will be talking about searching for galaxy cluster candidates from high-redshift HETDEX galaxies.
When examining this, the first question we have to ask is, what is dark energy? The short answer is that we don't know. We know that it can't be directly observed, but that it's everywhere, making up approximately 68% of our universe. We know that it's needed to explain why the expansion of our universe is accelerating rather than being overcome by gravity, slowing and eventually beginning to collapse in upon itself, but we don't have a precise definition.
We do have some ways of finding it. Dark energy is really just how the universe expands, and we can observe that through supernova, distortions, and sound waves. Some exploding stars that are known as supernova were observed to be fainter than expected. The explanation for the difference in expected light led scientists to believe that the universe is expanding faster as it ages. Type 1a supernova are instrumental to understanding the expansion of the universe. The destruction of a white dwarf star is fairly predictable, so by measuring the observable brightness and the true brightness, we can find the distance of the supernova. We then measure how fast the star is moving away from the Earth by evaluating the redshift, the stretching of light waves caused by the expanding universe. As light waves travel throughout the universe, they get warped by the gravity of intervening objects. This is called gravitational lensing. A weak lensing produces a subtle distortion in the shape of a galaxy, an effect that could only be observed through the analysis of millions of galaxies. Such patterns map a three-dimensional chart of the distribution of matter throughout the universe. Dark energy causes the space between matter to get larger, thus causing the expansion of the universe and the distribution of matter to be thinner. Different theories for dark energy require different histories of expansion to occur in the universe, and so the determination of how the universe has expanded will assist in the determination of the correct theory on what dark energy is. We also look at sound waves measured by HETDEX. Sound waves originating from the dense early universe helped matter begin to clump together. The technical term for these sound waves is baryonic acoustic oscillation and can be considered as the basic measuring unit of the distribution of matter in the cosmos. The more waves of pressure in an area, the more stars and galaxies will form in that area. Scientists are able to search for signs of these sound waves with HETDEX in an attempt to find the imprint of these ancient sound waves. By measuring the imprint of these sound waves and comparing them to the relative strength of dark energy at different epochs, being the speed of the universe expands, we can assess what dark energy truly is.
All our data from this project comes from the Hobart-Eberly Telescope Dark Energy Observation Project, or HETDEX, at UT Austin's McDonald Observatory. It surveys over 1 million non-targeted galaxies, and every exposure produces approximately 34,000 spectra. The thing that makes this so exciting is just how much data there is and how old it is. That creates a problem. There's too much data to be processed, and so scientists at UT Austin are relying on citizen scientists to help start to process it and train an AI algorithm to do the same.
Citizen science is so important because the massive amount of data necessitates participation from volunteers. This also allows qualified scientists to spend more time on pressing issues. Dark Energy Explorers, the platform we used, has collected approximately 1.3 million classifications, has 14,124 volunteers, has reached over 85 countries, and is 91% complete with the HETDEX dataset.
To explain how we understand and classify these galaxies, you're going to have to look at the image to the right. Each signal is a composite of several spectra tiling a circular region of the sky. Each colored box contains a small part of the spectrum where we have detected a signal. The black dots are the signal, while the gray background is noise. These dots are photons that have been traveling for up to 11 billion years, coming from a galaxy that's producing a lot of stars, and they finally made it into our instrument. The top left box in the black outline is the sum of all the colored boxes. The more clear and strong the dot appears in this box, the better we trust the signal. Additionally, it's important to see signal in individual fiber spectra. If we see dots in two or more of the colored boxes, we have high confidence that the signal is real. The boxes in the upper right show optical fiber positions. The bottom left box displays resultant 1D spectrum and emission line fit. It shows redshift and distance. We use spectral lines to determine if an astronomical object is real or fake, fake being its noise from the telescope or other instrument. Spectral lines are often used to identify atoms and molecules. A shift in the position of the spectral lines in our data tells us the distance to the galaxy, so we can create a three-dimensional map of the night sky. The brighter the yellow dot in the line flux map, the more likely the galaxy is real. A yellow line, however, displays the data error.
Part of our research involved taking our own part into citizen science. To sort through HETDEX data, we distinguish between background noise, bad data, galaxies, and black holes. While looking for bad data, we looked for missing sections of optical fibers. You can see in the first image, there are missing pieces of data that look like small gray rectangles. Bad data is also identified by repeating sections in the line flux map or within the fiber images. It's easy to identify because it almost looks like a glitch in the image. While identifying galaxies, we are looking for a clear circular or ovular shape in at least two of the fiber images. You can see in the middle image, there is a clear circle in the combined fiber image. While looking at the smaller fiber images, there's clear evidence of the shape of the galaxy because the dark figure shows up in multiple slides. Taking a look at the spectral lines, there also must be a clear correlation between a line of best fit and the spectral lines. In the line flux map in the bottom right corner, there must also be a clear yellow dot within the red square. If you're lucky enough to see a black hole, you'll see an elongated black shape in the optical fiber images. The spectral lines will usually follow an elongated curve, but in the ones that we found, the curve ended up being taller with less area. When you don't find bad data, a galaxy, or a black hole, the data is most likely background noise. There will be no clear dot in the optical fiber images or in the line flux map, and the spectral lines will not follow a clear curve. If none of the criteria for galaxies or black holes apply to the image, it is most likely background noise to throw back into the system. In only a couple hours, we sorted through a total of 2,140 data points. We discovered 899 galaxies, which is also equivalent to 42% of our entire data set. We also discovered 4 black holes, equivalent to 0.2% of our entire data set. The rest of our data was background noise or bad data, which we had to throw back into the system. This is why citizen science is so important. As a team of 4, we were able to sort through over 2,000 data points in only a few hours.
In addition to citizen science, we analyzed 139,188 galaxies from HETDEX Source Catalog 1, separated into 6 different declination ranges. Declination is the celestial equivalent of latitude. The full dataset included over 200,000 objects. To narrow down this massive dataset, we removed all stars, as well as galaxies, with a redshift confidence of below 0.4. What we're looking at with this data are high spectroscopic redshift galaxies of z equals 1.9 to z equals 3.5, meaning that they're very old and very far away. Currently, the farthest known galaxy cluster is located at a redshift of 2.5, and the farthest supercluster is located at 1.27, and we're looking way beyond that. The first image we have is a 2D polar graph of all 140,000 galaxies. Because we couldn't model in 3D, we examined these galaxies separately in 2 planes. We start here with groups of declination. The circular rings you can see radiating outward from the origin are different redshifts or distances, which were multiplied by a factor of 10 for graph simplicity. The straight lines stretching outward are different right ascension angles, which are the celestial equivalent of longitude. You might be wondering about the blank spaces within the graph. Since this data is from 6 years into the 8-year survey, some parts of the sky have not been explored by HETDEX. Additionally, low confidence galaxies as well as all stars were removed from the full release dataset. Here we have a zoomed out graph of declination group 6. It has very few points, less than 1,000, so it's too hard to identify any clumping in this graph. Let's skip past it. Let's take a closer look instead at declination group 4, which are 52 degrees to 54 degrees. Here is our zoomed out graph. The dark, dense black triangle near the origin is relatively nearby galaxies with low redshifts that have already been studied. We're focusing on the outside section, about 1.5 to 3 on this graph. Recall that these numbers have been multiplied by a factor of 10 for simplicity. Here is our zoomed in model of declination group 4. The red circles surround visually identified clumping, and the lines through them are different right ascension angles. The top right ascension line on this graph has a considerable number of possible clusters, so let's investigate it further. We will use the inverse tangent of the green point and add 180 degrees because it's in the third quadrant to find that this line is at an angle of 214 degrees. Now we double check that this is indeed a clumping by flipping our graph. This graph is grouped in a range of right ascension centered around our previous calculation of 214, and the red line is a line of declination. We will use trigonometry once again to find the angle of this line at 52, which falls exactly within the group 4 declination that we originally found our 214-degree right ascension at. This proves that there is indeed a galaxy cluster candidate at the celestial coordinates of declination 52 degrees and right ascension 214 degrees. However, we can't know that this is indeed a cluster without analyzing other variables, such as velocity dispersion and density. We have checked the x-plane and the y-plane, so we have one last step to verify that this is a cluster candidate. These graphs show the distribution of galaxies in the sky grouped by redshift. Redshift is the distance, so it would be the z-axis of our hypothetical 3D graph. The center point for each graph is 214.52, our celestial coordinates, in arc minutes. These images show why we need more refinement in our search. We still see clumping around these coordinates, meaning that we were very close to the right numbers, but not exactly on the dot. With further research and greater computational abilities, we can ideally get these coordinates down to the decimal.
I studied declination group 1, which was a group of galaxies with a declination of -5 to 5 degrees. I found clusters with a right ascension angle of 20 degrees. Once I found the other groups of galaxies with a right ascension angle of approximately 20 degrees, I found that they all fell into a declination of about -0.23 degrees. Realizing that this fits into the original dataset with a declination of -5 to 5 degrees and finding clumps along the declination plane, I was able to prove with little doubt that these galaxies are potential candidates for galaxy clumps. It is important to keep in mind the right ascension angle goes in a 360-degree counterclockwise circle, and the declination is in a range of 90 at the North Pole to -90 degrees in the South Pole, with the celestial equator being at a 0-degree declination. With this declination being about -0.23 degrees, this data set is right in line with our equator.
There is reasonable evidence of galaxy clumping candidates at high redshift galaxies, such as 1.9 is greater than z is greater than 3.5, from the Hobby-Eberly Telescope Dark Energy Experiment, also known as HETDEX survey. It is based on visual observations of clumping from 2D polar graphs of declination ranges and right ascensions. Over 30 possible clumpings were identified within the right ascension equals 20, declination equals 0.05, and right ascension equals 196, declination equals 54.5. Once again, it must be mentioned that we currently do not possess the computational power to validate these galaxy clumps, and these are merely candidates. Our experience.
My experience here at NASA Seas in UT Austin has been once in a lifetime. In addition to forming close friendships with some seriously stellar people, I've loved performing unique research on dark energy in far-off galaxies, something truly out of this world for a high schooler to be able to experience.
This experience has honestly pushed me to grow like nothing else. Every day I've come in to work with a ludicrously talented group of students. And even if we haven't been explicitly taught how to handle what we're doing, we know that we can figure it out, and that process will teach us more than any classroom setting.
This experience gave me an incredible opportunity to work with like-minded individuals on a shared interest. It opened my eyes to the field of astronomy too. I feel that I've not only gained technical knowledge on the subject of space science, but I've gained experience collaborating with interdisciplinary STEM focus groups.
My time at SEAS was an excellent opportunity to grow as a person and as an academic in a new and competitive environment. Being able to listen to experts in the industry about their work, the paths they followed to get where they are today, has been an incredibly useful tool and will be for more and for my future.
We want to thank the SEAS program, the Center for Space Research, UT Austin, NASA, and especially our incredible mentor, Dr. Judit, for putting this internship together and giving us this experience we've gained over the past 2 weeks. We know it'll impact us for a lifetime. Thank you.